Hello and welcome to the video lecture series brought to you by St. Andrews Institute of Technology and Management. My name is Ravinder. I'm an assistant professor with ETCE department and we are discussing the subject called Data Structures 2. Yesterday we have seen the introduction to the AVL trees, that is the balanced binary search trees. And today we are going to see how to insert a particular node in your AVL tree. Okay. Now, inserting an element into an AVL search tree in its first phase is similar to that of one used in binary search tree, that is your BST. But if after insertion of the element, the balance factor of any node in the tree is affected so as to render the binary search tree unbalanced, we sought we resort to the technique called rotations to restore the balance of the search tree. Now, as you now know that our AVL tree is actually height balanced BST. Now, yesterday we have seen that how to calculate the balance factor at each and every node. Now, if you are, as we know, that addition of a particular node, or we have discussed earlier, that addition of a particular node in a binary search tree can be done only at the leaf nodes, and same is with the case with AVLs. Okay, so in AVL tree also you can insert a particular node at its leaves all okay at its leaves only. So when you are going to add the leaf or a particular node in the at a particular leaf in your AVL tree, the height of that particular subtree is going to change. It is going to change drastically. And then again you have to calculate the balance factor at each and every node. And you will find that in some cases the balance factor tends to get outside of the permissible zone. That is, the balance factor may be some other value than the permissible values, that is 1, 0 and -1. So if the balance factor tends to move towards 2, 3, 4, or 5, in that case, your binary search tree will not be a balanced binary search tree or an AVL tree. Okay. So in that case, we have to resort to the techniques called rotations. Now, rotation is a technique. Let me add you to the slides. Yeah. So rotation is the technique through which we can achieve the balancing act of let's say the unbalanced tree actually self balances itself into an AVL tree. Let me again tell you that both of the balanced and unbalanced trees are actually your binary search trees, but whether that particular tree is AVL tree or not depends on the balanced factor, that is highest balanced factor. So after the addition, it may or may not be possible that your AVL tree will not remain a balanced height tree. So it will not remain a AVL tree, a legal AVL tree. So in that case, you have to do the operations called rotations, and after that rotation, the tree that has become unbalanced after the addition of a particular node will again become balanced. So the technique of again changing your unbalanced BST into an AVL tree is called rotations. Okay. Okay. So rotations are of few types. Rotation could be of single type and rotation could be of double type. So we have single rotations and we have double rotations. And then again, for single rotations, we have left rotation, right rotation, and for double rotation, we have left right rotation and right left rotation. Now today we are only going to discuss about your single rotations, that is left rotation and right rotation. Okay. Now, what is left rotation? Now left rotation is actually basically a rotation, and we are just going to see what is a rotation in actually. So it is also a type of rotation which is applicable if the inserted node is in the left subtree of node A. I have not misspelled left subtree two times or again repeated myself two times, but definition actually says that the inserting or inserted node is in the left subtree of node A. And in the same way, the right rotation is applicable to the cases where the inserted node is in the right subtree of node A. Okay. Now, to perform the rotation, it is necessary to identify a specific node A. Now, whose balance factor is neither 1, neither 0, or -1. Okay, so that means the balance factor of that particular node is not in the permissible limit. That is from -1 to 1. Okay, now that particular node which we have to find out is going to be the nearest ancestor to the inserted node on the path from inserted node to the root node. Okay, now this implies that all the nodes on the path from inserted node to A is a tree, let's say, or a node, will have their balance factor to be either 1 or 0 or -1. Okay, so that is the case of rotations. Now we are going to first see the case of left rotation. Now here it is. This is how a left rotation is going to be understood. Okay, just give me a second. Yeah. Now this is how a balanced or sorry, not balanced, but your left rotation is going to be done. Now here you can see in the first figure, you will see that we have a balanced avial search tree, and you can see that we have two nodes here. All of these three nodes that is of rectangular shape are actually of let's say are leaf nodes. You can consider them as leaf node, or you can consider them as subtrees, but these subtrees are as such that the balance factor at node B is actually 0. Okay, so let's say height of this left subtree is h and height of this right subtree is also h. So in that case, the balance factor will be h minus h, that is equal to 0. Now that is in the permissible limits that we want for an avial tree. Now at the node A, again, the balance factor is actually +1. Why it is so? Because the height at this subtree level is h. Then again, height of B will be h plus 1. I have shown you yesterday how to calculate the height, and the height of this right subtree of A is actually h. So h plus 1 minus h is actually equal to +1. Then again, this node A, you can call this particular node A as balanced, because balance factor that has been calculated at this particular node A is +1, which is in the permissible limit. So you can see that, you can say that this particular binary search tree is a height balanced binary search tree, or an AVL tree. Now comes the insertion of a node. Now let's say if we have inserted a node called BL in the left subtree of node or the root node. So I think you have now got the point why I have repeated myself of saying left subtree and left subtree. So we have inserted a node called BL to the left subtree of the left subnode of A. Okay. Now, as you know that when we add this one particular node, the height of this particular left subtree now becomes h plus 1, because we have one new member here, one new leaf node here. Now the h plus 1 height of this particular tree is h plus 1. So the height of B is now h plus 2. But the height of this right subtree of A still remains h. Now if you calculate the balance factor between these two level at this particular level for this node A, it is going to be h plus 2 minus h, that is 2 or plus 2. Now plus 2 or either minus 2 is not actually inside the permissible limits to be an AVL tree. So this particular binary search tree at this particular point is not a legal AVL tree, or you can say it is an unbalanced AVL tree. Now to again, as we know that we are actually using an AVL subtree as our data structures. So after insertion, due to the unbalancing factor, we again have to make or execute some operations to make it balanced again. Okay, so that is where our rotations will come into effect. Now left rotation means that addition is onto the left hand side, and then again rotation is from left hand side to the right hand side. So rotation is in clockwise direction. Now what will happen is this B will take place the place of your root node A. So that now B is your root node, and according to binary search tree rule, as you know that as you already know that B is to the left hand side of A, so it is absolutely clear that the value of B is actually less than A. So in that case, if B is your root node, in that case A will come to the right hand side. Now A has come to the right hand side of A, but now there is a problem. The problem is that this right hand side subtree of B has all the values greater than B. This is according to the rule of the AVL tree, but less than A. That is why they have ended up here. Okay, that is why they have ended up here. So all the nodes in this left subtree have value greater than B, but less than A. But after rotation, this particular subtree actually falls to the left hand side of B, and which is not possible if you follow the binary search tree rule. So in that case, what we have to do is we have to switch the loyalties. Now this particular right subtree, that is BR, has now switched its royalty towards the node A, which I have been shown here. So the complete rotation includes of two steps. First is the rotation part, in which your middle node, that is this particular node, has moved on a 1 point, and or you can see a clockwise rotation, and after that the switching of royalties. Now so switching of royalty has taken place. This BR, which is previously been associated with node B, is now been associated with node A, and it has came down that this particular left subtree, or all the nodes or a single node, whatever be it is, that is being associated to the right hand side of node B has now been associated to the left hand side of node A. So this is how you complete your left rotation. So next we are going to see one example here. Now suppose now this is your legal AVL tree. You can calculate the balance factor at each and every node. You will find out that they are in permissible limit. Now when you are going to insert 36 to 64, in that case the height of B will become, that is 1, 2, 3, and height of this particular 110 is still 1. So 3 minus 1 is again plus 2. In that case you can say that this node, this particular AVL tree is unbalanced at node A or node 96. So we have to perform the rotation. So the rotation will be performed as such that this 96 or the unbalanced node will come down one step towards the right hand side, that is it will move in a clockwise direction, and your 85 will now become, or your left hand side party will now become your root node. So 85 has taken the place of your root node, and 96 has came down. Now the switching of the loyalties, as you know that all the values of the nodes towards the left hand side must be less than 85. So in that case, this 90 will attach itself to node A, that is 96. So this is how your left rotation will take place. Okay. Now exactly opposite is your right rotation. Now in right rotation, there will be addition of a node towards the right subtree of your node A. Okay, so we have added one BR node towards the right subtree of B, which is actually the right subtree of node A. If after this addition, the balance factor at node A is now -2. Now let me again tell you that it is not always possible that your root node is the node which is actually unbalanced. It may be any internal node which could be unbalanced. In that case, the any internal node at which your balance factor or your nearest node which has a balance factor out of the range, that is 1, 0 and -1, at that particular node you have to perform the operation of rotation. It is in this particular example, as you can see, every time we have done an operation it is on the root node, but it is not mandatory, because in the definition I have told you that the nearest node which is unbalanced with respect to the node which you have added. Okay, so the nearest node which has been unbalanced due to the addition of node BR is actually A. Before that, all the nodes are balanced. That is, their balance factor is actually in the permissible limits of 1 and -1. Okay, so the rotation will always take place on that particular node which is nearest to the added node, and which is actually the first node which you have encountered while going up, and which has a balance factor which is actually outside of the permissible limits. So again, the rotation will take place and the royalty shift. In this case, the rotation will take place in anti-clockwise direction. So now at this time, your node A will step down and node B will become the root node, and the left subtree, that is BL, will switch its loyalties from node B to node A, as you can see in this case. So let's see an example. Now in this example, we have to insert node 65 to the node 56. At first, it is balanced. Now after addition of 65, you can see the first unbalanced node that you will encounter while heading up from the added node to the up is actually this node 34, which is again the root node, which I have already told you is not going to be the case every time. Okay, so please make sure. So while going from 65 to the up, the first node we are going to see which is actually unbalanced is the node at which the rotation will take place. So the rotation in this case will take place at root node 34. So 34 will step down towards the left hand side, that is the rotation in anti-clockwise direction. 44 will take place of the node A, that is it will become the root node now, and the 40th node, that is this particular node, will shift its loyalty from the node B to node A, which we have shown here. So this is how your left and right rotation will take place. Tomorrow we're going to see the mixture of left right and right left rotation. It is actually going to be a 3-step process. It is a lengthier rotation process, but after going through, if you have understood this particular topic, that is your left and right rotation, I don't think there is going to be an issue to understand these left right and right left rotations. So I'm going to end this lecture now. Thank you.